Welcome back to the deep dive. Today we're going to strip away absolutely everything.
Everything.
Yeah, I mean, no news, no politics, no complex history. We're going to focus entirely on a wooden table, a dark room, and two envelopes.
It kind of sounds like the opening scene of a noir film. or maybe some really stressful psychological experiment.
It's a bit of both, honestly. We are diving into the two envelopes paradox. And I have to say, looking at the research stack we have today, this is one of those topics that starts out looking like a totally simple parlor game and ends up, well, questioning the very fabric of how we make decisions.
Oh, it really does. It's a problem that has kept philosophers and mathematicians, economists, basically anyone who thinks about logic awake at night for decades.
Right.
Because it exposes a literal glitch in human logic, specifically how we deal with the concept of value when we are operating in total, absolute ignorance.
Total ignorance. The source material actually calls it the hidden cost of free money, which is, I mean, that's a hook if I've ever heard one.
For sure.
So let's just set the stage for the listener. I want you to imagine you are standing in that dark room. There is a table, and on the table are two envelopes.
Just two?
Right. They're identical, same size, same weight, same crisp white paper. You literally cannot tell them apart.
And here is the setup, the actual rules of the game. One envelope contains a certain amount of money.
Okay.
The other envelope contains exactly twice that amount. So we have a base amount, let's call it X, and another amount that is 2X.
But here is the catch, and this is the constraint that drives this entire paradox. You have absolutely no other context.
None at all.
You don't know who put the money there. You don't know if we're talking about, loose pennies or millions of dollars. It is a complete black box.
And that is the most critical part to remember here. Total information blackout. You know the relationship between the envelopes, that one is double the other, but you know absolutely nothing about the absolute values inside them.
Right. So you step up to the table, you pick one envelope at random, you hold it in your hand, and just for the sake of this deep dive, let's say you open it up.
Okay, let's open it.
You peek inside, and you find a crisp $100 bill.
Not a bad day. I mean, you walked in with nothing, now you have $100.
Yeah, but now comes the twist. The game isn't over. I look at you across the table, and I offer you a trade.
The wager.
Exactly. I say, you can walk away with that $100 right now, or you can swap it for the other envelope still sitting on the table.
The classic wager. Do you stick or do you twist?
Right. So the question is, what do you do?
Mm.
And more importantly, why do you do it? Because when I first read this, my gut reaction was immediate.
Let me guess. Your gut said to switch.
Oh, absolutely.
Oh.
I mean, I'm looking at my $100. I know the rules. The other envelope has either half of this amount or double this amount.
Right.
Right. So physically, the other envelope contains either $50 or $200.
Correct. Those are literally the only two possibilities allowed by the physics of the game.
So I naturally start doing the mental math. I'm weighing the risk. If I switch and I lose, I end up with $50. I've lost $50.
Which stings.
It stings, but I still have 50. But if I switch and win, I get $200. I've gained $100.
You're looking at the asymmetry of the payoff.
Exactly. The upside is double the downside. To me, that feels like what investors call positive asymmetry. Why would I stay put when the potential gain is twice as big as the potential loss? It feels like the universe is just offering me a massive discount on a gamble.
It's a very seductive argument. It feels super intuitive. You're risking $50 to make $100. Most gamblers would take those odds in a heartbeat.
Right, any day of the week.
But we're here to go deeper than just a gut check. Let's look at the actual math provided in our source material. Because there's a section here covering the expected value calculation, and it actually seems to back you up.
Okay, let's unpack that math.
Right.
Because usually when I follow my gut, a statistician comes along and tells me I'm being totally irrational. Yeah, but this time, it looks like the numbers are actually on my side.
Well, let's run the numbers and see. Expected value, or EV, is basically the average outcome if you played this game a million times. It's how rational machines make decisions.
Okay.
To calculate it, you take the probability of an outcome and you multiply it by the value of that outcome.
Simple enough.
So you're holding your $100, you're considering the other envelope. We established there are two scenarios. Scenario A, the other envelope holds $50.
Right.
And scenario B, the other envelope holds $200.
And since I have absolutely no clue which is which, and the envelopes are completely identical, I have to assume it's a coin flip. It's a 50-50 chance.
That is the standard assumption people make, so let's plug that into the formula. You have a 50% chance of getting $50. So 0.5 times 50 is 25.
Okay, 25.
And you have a 50% chance of getting $200. So 0.5 times 200 is 100.
Right.
Now add those two together.
25 plus 100 equals 125.
So the expected value of the unopened envelope sitting on the table is $125.
Wait, let me pause there. I am holding a literal $100 bill.
Yeah.
But the math says the envelope sitting on the table is theoretically worth 125.
Mathematically, yes. 125 is greater than 100. Therefore, a rational actor, someone just trying to maximize profit, must switch. The math dictates it.
It feels like magic. I've essentially created $25 of value out of thin air just by being willing to move my hand from one envelope to the other.
It certainly looks that way, doesn't it? The math is telling you that the unknown envelope is statistically richer than the known envelope.
So I switch, obviously. I'd be an absolute idiot not to.
Okay, let's play that out. You switch, you put down your $100, and you pick up the other envelope. You haven't opened it yet. You're just holding it.
Okay. I'm holding the new envelope. I'm feeling pretty good about my expected value.
Now, let me ask you a question. Would you like to switch back?
Why would I switch back? I just did the math. This one is worth more.
Is it? Let's look at your situation again. You are holding an envelope. You don't know what's in it. Let's call the amount inside amount B.
Amount B.
The other envelope, the one you just put down on the table, has either half of B or double B.
Oh no. I see where you're taking this.
If you run the expected value formula on your new holding, assuming the same 50-50 odds, the math is going to tell you the exact same thing.
You've got to be kidding me.
It will tell you that the envelope on the table, the one with the original $100 in it, is worth 1.25 times what you are holding right now.
So the math tells me to switch back.
And if you switch back, the math will tell you to switch again and again and again. You are now trapped in an infinite loop.
Wow.
You're just standing at a table, sweating, swapping envelopes back and forth forever, constantly convinced that the other one is better.
That is a huge problem.
Yeah.
That is what the source material refers to as the glitch in the matrix.
It is the definition of absurdity. Think about it. If switching is always better, purely based on the algebra, then you shouldn't have even needed to look at the $100 bill in the first place.
Right.
You should have just walked up to the table, picked an envelope, and immediately traded it for the other one without even peeking.
Which makes zero sense. If the envelopes are identical, one cannot be inherently more valuable than the other just because I'm not touching it. That's just magical thinking.
Exactly. Logic that suggests swapping forever is not logic. It is a paradox. It means something is deeply broken in the machine.
Okay, so help me fix the machine. Because the arithmetic was incredibly simple. 0.5 times 50 plus 0.5 times 200 equals 125. You can't argue with multiplication.
No, you can't.
So where is the lie?
The lie isn't in the multiplication. The arithmetic is completely flawless. The lie is in the assumption that let you do the multiplication in the first place. We need to look at the part of our research titled The Hidden Assumption.
Okay, detective time. What did we miss?
We breezed past the most critical part of the setup. You said, since I don't know which is which, I assume it's a coin flip. 50-50.
That's standard, isn't it? If you don't know, you assume equal probability. It's unbiased.
That is called the principle of indifference, and in this specific case, it is dead wrong. The source material calls this unjustified symmetry.
Unjustified. But I have no information. Why is it unjustified to be neutral?
Because you're confusing, I don't know, with it is equal. Those are two very, very different things.
Okay, explain that.
By assigning a 50-50 probability, you are implicitly claiming you know something about how the money was put in the envelopes.
How so? I thought I was claiming I knew nothing.
To say there is a 50% chance the other envelope has 200 and a 50% chance it has 50, you're assuming a specific distribution of money in the world. You're assuming that the person running the game is just as likely to have put $200 in a bag as $50.
Okay, that seems reasonable, though.
But if you follow that logic all the way down, you end up assuming that every single amount of money is equally likely. $5, $5 million, $5 trillion.
Oh, that's the uniform distribution mentioned in the notes.
Right. But think about what a uniform distribution over all numbers actually implies. It implies there is an infinite amount of money.
Right.
It implies that if I pick a number between 1 and infinity, I am just as likely to pick a number with 100 zeros as I am to pick the number 10.
Which is physically impossible. There isn't infinite money in the universe.
Precisely. You cannot have a uniform probability over an infinite range. It doesn't sum to 100%. It literally breaks the laws of probability. So your 50-50 guess wasn't just a harmless guess. It was a mathematical impossibility.
Wow. So just because I don't know the odds doesn't mean the odds are 50-50.
Exactly. And this brings us to the real heavy hitter of this deep dive. The actual solution to the paradox comes from a field called Bayesian statistics.
Ah, the Bayesian refutation. It sounds like the title of a spy novel, but break it down for us.
It's named after Thomas Bayes, who dealt with how we update our beliefs based on new evidence. The Bayesian perspective basically says you cannot calculate the probability of the other envelope without a prior.
A prior, meaning a model of how the money got there in the first place.
Exactly. We need to know the context. We need to know the system.
Right. Let's look at the probability machine graphic from the sources. It asks, where did the money come from? Because in the real world, amounts of money are not distributed evenly. Small numbers are super common. Huge numbers are incredibly rare.
Exactly. I mean, you have a lot more $5 bills in your life than you do $100 bills.
Definitely. And I've never even seen $1 million bill.
So real-world money follows a tapering distribution. As the numbers get bigger, the probability of seeing them gets much smaller. Now let's apply that back to our game. You opened your envelope and you found $100.
Okay.
We have to ask, is that $100 the bottom half of a 100 and 200 pair? Or is it the top half of a 50 and 100 pair?
Okay, I'm following you.
In a world where smaller numbers are more common, which pair is more likely to exist? The pair involving 50 and 100, or the pair involving 100 and 200?
Well, smaller numbers are more common, so the 50 and 100 pair should be more likely to exist than the 100-200 pair.
Exactly. Because $50 is more common than $200, it is statistically more probable that you are currently holding the larger amount of a smaller pair rather than the smaller amount of a larger pair.
Wait, this flips the entire thing on its head.
It really does. That 50-50 assumption is just gone. The odds are actually tilted. It might be a 60% chance you have the high envelope and only a 40% chance you have the low one.
And if I'm more likely to be holding the high envelope...
And switching, it's a terrible idea.
Whoa. So the math, the real math, not the simplified gut check math, actually supports sticking with what you have.
In most realistic scenarios, yes. If you assume the money comes from a finite budget or a real-world economy, finding a specific amount usually implies you are closer to the ceiling of that pair than the floor.
It's honestly simpler than I expected, but also so much deeper.
Let's make it even more concrete. The notes have this great example called the budget limit. Imagine the game show host has a strict budget of $150 maximum per envelope.
Okay, a hard ceiling at 150.
You open your envelope and see $100. Scenario A, the other envelope has 50. Is that possible?
Yes, 50 is under the limit.
Scenario B, the other envelope has 200. Is that possible?
No, that breaks the budget entirely.
So in that specific case, the probability of the other envelope having $200 is literally zero. You have a 100% chance of losing money if you switch.
Right, so my expected value calculation, the one that promised me a free $125, was hallucinating. It was giving me credit for a $200 payout that was physically impossible.
Exactly. It was calculation without context. And calculation without context isn't math, it's gambling.
That is the quote of the day right there. Calculation without context isn't math, it's gambling. It's amazing how much depends on that one hidden assumption of how the numbers are generated. If you don't know the distribution, you just can't calculate the return.
And that leads us perfectly to the so what portion of our show. Because I know some listeners are out there thinking, I am rarely offered mysterious envelopes of cash in a dark room. Why should I care?
Yeah, usually when someone hands me an envelope, it's just a bill.
But you're an investor, aren't you? Or at least you make decisions about the future. The section titled The Investor's Dilemma makes a really direct connection here. The two envelopes paradox is a perfect analogy for investing decisions made without knowing the underlying distribution of outcomes.
Okay, let's unpack this for the listener's portfolio.
Think about the stock market or maybe a startup investment. You are very often presented with a projection. Something like, base case, we make 2x, bull case, we make 10x, worst case, we lose our 1x.
And they usually assign probabilities to those, right?
Eh,
Like, we think there's a 50% chance of the bull case happening.
Right, but you have to ask, where did that 50% come from? Is it based on a rigorous real-world analysis of the distribution of similar companies? Or is it just the principle of indifference wearing a suit? You know, we don't know what's going to happen, so let's just call it 50-50.
Oh, I see. We treat the unknown as a coin flip.
Exactly. And just like in the paradox, if you assume a coin flip in a system that actually has fat tails or hidden limits, your expected value calculation is going to be total junk.
The notes mention fat tails versus Gaussian curves. That's the idea that extreme events happen way more often than we predict.
Right. Traditional finance very often uses the bell curve, the Gaussian distribution. It assumes things generally stay near the average, but the real world is incredibly messy. If you're betting on something that has a power law distribution like tech startups or crypto, things like that, your intuition about averages is going to be dead wrong.
Because in a power law, the big numbers are way, way bigger, but also way rarer.
Exactly. If you calculate your return assuming a safe, predictable bell curve, but the reality is a highly volatile power law, you might think you're holding the $50 envelope looking at a $200 upside, when in reality, you're holding the $100 envelope standing right on the edge of a cliff.
So the real takeaway here is about auditing your own certainty.
It is. It's about asking, what is my prior? Before I run the numbers, what do I actually believe about the system that's generating these numbers? If you can't answer that, put the calculator away. You aren't ready to do the math.
That is a tough pill to swallow for data-driven people.
Ah.
I mean, we love our spreadsheets. We love to plug in a probability and just get a clean decision out of it. But you're saying the spreadsheet itself might be the trap.
The spreadsheet is the envelope. It
Well,
looks objective. It feels sturdy and safe. But if the inputs are based on unjustified symmetry, it will lead you confidently off a cliff.
we've covered a lot of ground here today. We started with a simple parlor game, realized we were trapped in an infinite loop of logic, and then had to use Bayesian statistics just to climb our way out.
It's quite a journey. And I think it shows that intuition is a really powerful tool, but it desperately needs to be calibrated. The two envelopes paradox isn't really about money at all. It's about information.
Right.
It shows that the value of a decision is completely inseparable from the information you have about the context.
Context is king. I really like that.
Yeah.
Well, before we wrap up, I want to leave the listener with a final provocative thought from our source material. It's a question that's a bit uncomfortable, but I think it's highly necessary.
It's a great one to end on.
The question is, where else in your life are you assuming a 50-50 chance, simply because you don't know the true odds? Is it a career move? A relationship decision? A new investment?
That is the dangerous comfort of ignorance. We say, oh, it could go either way, when in reality the die is already loaded. We just haven't looked at the table closely enough to realize it.
So, this week, when you're facing a decision with two options, don't just look at the envelopes. Look at the table. Look at the room. Define your distribution before you calculate your return. Thanks for listening to The Deep Dive. We'll catch you on the next one.
Goodbye, everyone. Keep thinking.